back of the worksheet, and I know that many of you got to some of these where vectors are going in different directions and you were like, wait a minute, I don't know how to do these. And I said, hey, hold up, we'll get to those. In chapter 2, which you were assigned to read in 2.5, it talks about how we combine vectors right here, right? Like we did these problems. 300 newtons is going to be divided if there's two supports evenly into the 150 and the 150, which we just did one of those. Well, that's the easy part, right? So combining vectors is quite simple when they're parallel, but if they're all in the same direction, we just add those up. But if they're in opposite directions, we subtract, right? That's pretty easy. We've talked about that. That's what we've done so far. Now, here's where it gets more complicated. The sum of two or more vectors, well, we call them the resultant. But what if the vectors act at an angle to each other? So consider this example right here, where little Nellie is hanging by a pair of ropes, and they are not parallel to each other, and they're not opposite to each other. There's still a way to solve for this. To find the resultant of non-parallel vectors, we use something called the parallelogram rule. A parallelogram is like a rectangle or a square where there's two sets of parallel sides. To find the resultant of two non-parallel vectors, construct a parallelogram wherein the two vectors are the adjacent sides and the diagonal of the parallelogram shows the resultant. So we'll kind of get to what that means. We consider this like, this is a problem like what we're going to do second in this second problem right here, okay? So the diagonal right here, this is a resultant of the forces. In order to find this, we draw the other two sides to make a parallelogram, and we can connect that vector right there. So we construct this parallelogram, and we use this diagonal as the resultant, okay? In the special case of two perpendicular vectors that are equal in magnitude, the parallelogram is a square. This is a square. Then we have a rectangle. We also have like these squished parallelogram, like a diamond, where there is acute or obtuse angles. This angle is not a right angle. And those are also parallelograms. Here's another example of one of those over here. So if we were going to solve for the diagonal in a square, we have to use a little geometry. Since any square, the length of the diagonal is the square root of 2, or 1.414 times one of the sides. The resultant is the square root of 2 times one of the vectors. For example, the resultant of two equal vectors of a magnitude of 100 acting at right angles to each other would be 141.4, because you took 100 times 1.414, multiplied those together, that would be the resultant of multiplying 100 times this. That would give us this result if this vector was 100 and it was a square. This only works for a square, okay? In order to find the resultant for a rectangle, we have to use a little something called the Pythagorean theorem. There's a lot of rules about triangles that you're going to be asked to solve for. And what I want you to do is know that these relationships, we've proven them again and again and again, and they're kind of like little puzzlers, but there's ways to solve them. And remember that math is just a code. And if we practice and we go slow, you're gonna be just fine, okay? So let's take a look at some of these vectors, and we'll try, at least what it's asking us to do is to fill in the magnitude of each of these forces. If we don't know the magnitude, then at minimum we can do just using the vector, we can just draw the vector, right? Like that's gonna get you at least some of the way there. Okay, so these guys are going in opposite directions. We should know this one. These only have magnitude and they don't have a unit, so you guys are off the hook on that. The net force of this one is 0, as we know they're going in opposite directions. But this guy right here, this is my resultant. Okay, here's what's crazy. If this side is 3 and this side is 4, that means that this is also 4. And there's a little special triangle. When it's a right triangle, when this side is 3 and this side is 4, I know this side. It's 5. That's because I memorized it. That's called a 3, 4, 5 triangle. It's just a cool thing about right angles and right triangles is that if this side is 3 and that side is 4, that is going to be 5. It's just how it works mathematically. It's a cool trick to learn. Okay, here we go. So over here, this one's tricky, right? What do we know about this guy? We have to take this away. So what's our resulting vector right here is 3. And if I've taken away 2, and I've got this parallel right here, I know that now I have a 3, 4, oh, what do I have? Another 3, 4, 5. Why didn't I use this 5 here? I didn't use this 5 because I've got 2 going in the opposite direction. So my resultant for my right left is 3. And in order to solve my overall system resultant, I need to find out that side of the triangle right there. Okay, moving down. This one, when I make my parallelogram, I ought to notice something. If this side is 7 and this side is 7 and this side is 7, and okay, I didn't draw it perfect, but this side is also 7, that's a square. That means that my resultant is going to be 7 times the square root of 2, or like it said in the book, so right here, 7 times 1.414. All right. And I cannot believe you guys don't have to do units. That's crazy. All right. As you can see, plug it into a calculator and I end up with 9.898. 9.898, which I can round up, but I'm gonna leave it like that, just to let you know what's going on there. All right, let's head back up to the top here. This one's nice and easy, right? What is our resulting force? We would take the 4 and we can add a -3 because this vector is going in the opposite direction. So 4 plus a -3 is 1. On the next one, this is where I'm going to use that parallelogram rule again. And you guessed it, another 3, 4, 5, 3 on this side, 4 on this side. So that means that my resultant hypotenuse, there's a fancy word for you, is 5. Okay. Similar problem, huh? I see a 2 and a 5. I'm going to take the 2 from the 5, and I have left. But if I take this little vector right here, and I actually overlay it on this vector, it's going to take me to the place I need to be for my resulting vector on this part of the system, which is 3. Then from here, I could draw my parallelogram, get my resultant. So if this is 3 and this is 4, you guessed it, that is 5 again. All right. 10. If I take this vector, I could just pick it up and overlay it on this vector. It's going to take me back to here. That is going to be 7 because 10 minus 3 is 7, right? 7 and 7. Oh, it looks just like this one. I've already done the math on that. That's another square. So my resultant, I'm going to draw my resultant, and it is 9.898. All right, now we have some a little more complicated matters. Let's take a look. I'm gonna split it up, and we'll do these last two in another installment because we have to go back into the book and apply the parallelogram rule when we are working with angles that aren't right angles. And we'll take a look at how to solve that in the next video.